So let's just take a quick look at water. You have oxygen, which receives its electrons from hydrogen, or you could say, shares its electrons with hydrogen. Now, if you look at this molecule here, you'll notice that we have these little symbols here. This denotes a partial positive. This denotes a partial negative. So negative, we could just refer to the negative symbol as relating to negatively charged things, such as electrons. And the positive, those are going to relate, again, to electrons, which is the absence of electron, right? If you have less negative, you're therefore more positive. Now, one of the properties of oxygen is that it is very electronegative, meaning that its nucleus has a strong pull towards electrons. And then hydrogens, actually, their nucleus is not as electronegative as oxygen. And so what happens when your hydrogens and oxygen form a covalent bond, that sharing of electrons isn't shared 50-50 or 50%, 50%. What's going to happen is those electrons will gravitate closer to the nucleus of oxygen preferentially, giving it a partial negative charge, as opposed to the hydrogens where the electrons gravitate farther away from it than they otherwise would individually, or not when they're not associated with a bond, giving them a partial positive charge. So this is actually what makes water polar. So looking at the definition of polar, and again, this should be kind of review from maybe previous bio courses. Your polar molecules are going to be molecules where part of the molecule is more positive, or they have a partial positive, and part of the molecule is going to be more negative, which is going to contain a partial negative. So in this case, because you have a partial negative charge on the oxygen and partial positive charges on the hydrogens, this is therefore a polar molecule. So unequal electron distribution. All right, so as a general rule of thumb, this is actually going to be very important, especially when we get into proteins and the way they interact with their environment. Polar molecules are hydrophilic. So philic means lover of. Hydro means you could associate the word or the root hydro with water. So water loving is what that translates to. So things that are polar are going to love water. And that's because of the general rule of thumb that like dissolves like. Polar stuff likes to hang out around polar stuff. Non-polar stuff likes to hang out around non-polar stuff. And so if you're polar, you're going to love water because water is polar too. So polar stuff is going to dissolve within water. So they dissolve in water. So things like ethanol, things like sugar, those things will completely dissolve within water. Now, non-polar stuff, as I mentioned earlier, likes to hang out around non-polar stuff. So because water is polar, non-polar stuff is not going to like water. So they're going to be hydrophobic. They're going to be afraid of water. They're going to want to hang out around other non-polar things. So your non-polar, some examples of non-polar substance would be oils and methane. So for example, let's say we mix some water, which is polar, and some non-polar stuff like oil, we mix them together. What's going to happen is your like is going to hang out around like stuff. Your polar molecules are going to hang out around other polar molecules, and your non-polar molecules are going to hang out around other non-polar molecules. And so what you get is this aggregation of your non-polar stuff together. So if you see here, we have these globs of non-polar stuff, and then you have the water kind of, hanging out around it, which is going to hang out with other water. So that's a very important concept to know moving forward. So let's talk about how, your ionic compounds could dissolve in water. So we could take, some table salt, sodium chloride. So that's just your sodium bound to chloride because of the disparity in their charges. You form, crystal structures. So here's, the green guys. The green blobs are your chloride ions, and then the purple blobs are your sodium ions. You drop some of that into some water. What's going to happen, if you remember, your water molecules, the oxygens, are going to have a partial negative charge. And if you remember, your sodium, when it's in ion form, is going to have a positive charge. And so what happens is those partial negatives on the oxygen are going to be drawn to that positively charged ion. And so what happens is the water will completely encapsulate your sodium ions individually. separating them from your chloride ions. And so now you have this sodium, this positively charged sodium, enshrouded by water. And then in a similar way, your chloride ions, which are going to be negatively charged, are going to attract the partial positives of all of these hydrogens. And so in the same way, water will enshroud your chloride ions, kind of separating them from one another. So that's what happens when you drop some sodium chloride or some table salt into water. You get, each of the individual atoms being, pulled apart from one another. All right. So hydrogen bonds, let's talk about hydrogen bonds. So they're usually going to involve hydrogen, and they're usually going to involve the partial positive on hydrogen being attracted to a partial negative on something else. So hydrogen bonds may form between atoms with polar covalent bonds. So if you looked at water, or when we looked at water, those were forms of polar covalent bonds. They were covalent bonds, but they were covalent bonds in which the electrons were unevenly distributed. They gravitated more towards oxygen, therefore it's a polar covalent bond. So the partial negative portion on one molecule is going to have a weak attraction to the partial positive charge on the portion of hydrogen on another molecule. So hydrogen bonds don't necessarily share or exchange electrons, but it's the intermolecular forces that hold them together. So if you look at water, your hydrogens have a partial positive. Those are going to be drawn to the partial negative on the partial negative on the oxygen of other water molecules. We would actually call this cohesion because that's water on water action. Now we can just pretend like these are two proteins, for example. So you have a nitrogen bound to a hydrogen. Nitrogen's actually going to have like a higher electronegativity than hydrogen. So you're going to actually have a polar covalent bond here. And so you have a partial positive on this hydrogen. And that's going to be drawn to the partial negative on this oxygen here, doubly bound to carbon. So hydrogen bonds are going to be composed of, or they're going to be involved in, there are going to be bonds between two molecules that contain polar covalent bonds. So partial negative attracted to partial positive. And it's always going to involve a hydrogen. Okay, so let's look closer at water. Not too close though. So water hydrogen bonds. So water is going to exist in nature in three different states. When it's solid, its hydrogen bonds are actually further apart, giving it a lower density. When it's liquid, its hydrogen bonds are actually going to be shorter. So the water molecules are actually going to be closer to each other, giving it a higher density. Now gas, you don't really have much hydrogen bond happening, and so those are going to be very low density, the lowest density. So if you look here, because your solid water or your ice has larger, you could say longer hydrogen bonds, therefore giving it lower density, that's the reason why ice will float on top of water. Because when you're taking anything, the more dense material will actually sink, and the least dense material will float on top of the more dense material. All right, so water, as we kind of talked about, ice will float. And typically what can happen is, when you get a pond that freezes over, that ice sheet over top of that pond will insulate the underside of the pond. So another property of water is that it holds heat well. It's a great temperature buffer. That's why when we walk outside, we don't instantly boil up, and we also don't instantly freeze. It's because it takes a lot of energy to actually change the temperature of water. So ocean temperature is typically static for that reason. And then another property of water is that it can participate in evaporative cooling. So when we sweat, the water will carry away heat. Now another thing about water, we already talked about cohesion. So cohesion is water on water action. So that's water being attracted to other water molecules. But adhesion, that's going to be water's attraction to things other than water. So in the case of your xylem cells within plants, this is kind of like the vasculature of plants. Xylem is like the veins that carry water and minerals throughout the plant, you're going to have, it's going to have a lot of water in it. And so if you look closely, the water is going to be attracted to water through cohesion, but then you have water being attracted to, like the cell wall, so adhesion. So you have water, which attracts water, and then that water is going to be attracted to the cell wall, and then it's going to attract water, and then it's going to be attracted to the cell wall through adhesion, and then water. And so in doing that, your water could actually climb up against gravity. We call that capillary action, by the use of cohesion and adhesion. All right, so more information about water. Water's pretty important. So water is a great solvent of things that are soluble in water. So polar substances, or ions in this case, or salts. So so water, if it is a medium, or water is the medium, for all aqueous solutions, because all an aqueous solution is a solution that water is the solvent. So we have two terms here. Water, in this case, is the solvent. The solvent is the substance dissolving something. The solute, that's going to be the substance that is being dissolved. So we could say that we drop some table salt into water. The table salt is the solute. The solvent is the water. The solution is an aqueous solution because water is the solvent. All right, so we have acids and bases. As a general rule of thumb, we're going to speak very generally about acids and bases. We're not going to go too deep into the chemistry here, but as a general rule of thumb, acids are going to be things that donate or release hydrogen ions into a solution. And then as a general rule of thumb, bases are going to be substances that accept hydrogens within a solution or donate hydroxide ions. So water could be potentially a weak acid, and it could also potentially be a weak base. All right, so acids and bases react to make a salt. So here, if we look at this chemical reaction, you have hydrochloric acid. This is the acid. It's going to donate this hydrogen. And then you have this potassium hydroxide. So you have potassium here, and then this hydroxide here. That's the base. So this is going to donate this hydroxide ion, and then that hydroxide ion could actually take up a hydrogen. And so if you mix those two things together, what happens is you get this, hydroxide ion, and it's going to take up this hydrogen here. That's going to make H2O. And then that charged particle, you could say that ion, potassium ion, is going to be attracted to that chloride ion. So this is a salt dissolved in water, an aqueous solution. So here you have hydrochloric acid, and you have potassium hydroxide. You mix them together, you get potassium chloride in a water solution, in an aqueous solution. All right, so pH scale. This should be pretty familiar. It's representative of the hydrogen concentration in relation to the hydroxide concentration. And so usually when you see brackets around something, generally, in science, that's just going to mean the concentration of something. So the concentration of hydrogen is equal to the concentration of hydroxide ion at pH 7. That's pretty much just saying that at pH 7, you are neutral. You are completely neutral. Your hydrogen ion concentration, or your proton concentration, is equal to your hydroxide concentration. Now, if you are less than 7, so as you get to lower numbers, that means you have more hydrogen ions, making you acidic. So as you go lower in the concentration, that would be this way. Yeah, so lower in the pH scale means you have more hydrogen. Higher in the pH scale means you have less hydrogen, or you could even say more hydroxide. So you're more alkaline. So 7 is neutral, 7 to 14 is alkaline, and 7 to 0 is acidic. All right, so buffers, their job is to, at least in terms of pH buffers, what they're going to do is maintain pH balance. And usually your buffers are going to be a mixture of weak acids and weak bases, or a complementary weak base, so that any additional acid or base will actually be disabled, or you could even say neutralized, and have very little impact on the overall pH of the solution. So if we look here, you could say that this little teal dot is going to be the hydrogen ion, because this is an acid, so it has the potential to donate a hydrogen. And then your base looks like, here's your molecule, and it's negatively charged, so it's kind of primed and ready to receive a hydrogen ion. So it's going to remove the hydrogen ions from solution, and then your acids are going to donate hydrogen ions to the solution. And so let's say you have a mixture of your weak acids and weak bases in a solution. What can happen is, if you, let's say for example, add acid to the solution, what's going to happen is your weak base is going to take up those hydrogen ions, reducing, or you could say neutralizing, that change in pH. Now, if let's say you add something that brings a bunch of hydroxide ions into the solution, well, what would happen is your weak acid could donate its hydrogens, neutralizing those hydroxides and making water. So buffers lessen the impact of a solution on another solution, or they lessen the impact of a base or an acid addition to a solution, to keep its pH more consistent. All right.